Morning, guys. I hope you're doing well. First thing I wanted to talk just a second about the test. So I have graded most of it. I am still making some adjustments because there were a couple of questions where you didn't get enough information. So those are going to be made bonus questions for 2 of them, and then one of them will be a partial grade because everybody answered 3 of the columns. So I'm going to grade just those 3 and leave the other 2. I hope that that will be fine with you guys. So that means the test will be worth less points, but it will still count as a full test. So the other thing about the test is I need to take a look at some of the stuff that I got in because it didn't look the way I expected. And I need to make some comments to the people that had that situation so that we can talk about how that can't really happen going forward. But of course, because I hadn't said anything about it, there's not anything I can do at this point. That's on me. So part of that is going to be a discussion about why does it look different. So I will want to talk to you, anybody who had that situation, and see if we can sort that out. Okay. As I stated in the email that I sent and the additions that I've made, you need to make sure that the work that's on your scratch work will support the answers that were put into the test. If it looks completely different, that's a problem. So I hope that that's self-explanatory. All right. Now, the other thing I wanted to talk about is where we are, where we should be, and what we're going to do to get us back on track. So, as I think you know, we're a little bit behind. So today we're going to be talking about complex science because I had reversed the order of these 2. I told you that I did that. So we're going to be talking about complex science. Then we need to talk about some stuff that's related to electrochemistry, so redox and voltaic cells. That's the material that's on the second test. Okay, so that will cover everything for the second test. Now, that means we'll probably be needing to talk about both of these on Monday, and I don't think that will be a problem. I don't, because they take a lot less time. There's math there, but it's not nearly as complicated. So generally, we don't need as much time to discuss it. Now, if that doesn't work, then we're going to have to push the test back. That's all there is to it. Unfortunately, on the 12th, there is not supposed to be a lab or a lecture section. So that, I think, is actually the Wednesday, which is so that means that we have one less day to talk about things. So I'm probably going to move this test to the weekend anyway, but aside from that, we may move it further. So I will take a look at moving it at least to the weekend because I think it's over the week right now, and I don't really like that anyway.
So are we going to be we're going to be covering the redox reactions that we have an assignment on this weekend?
Yes.
Okay.
I believe I will get to that today. And if we don't, then I will move that due date. Because that's not on you, that's on me. So if we don't get to that, and I may just move that due date anyway, because it might make sense to. So I'll take a look at that as well. Thank you for bringing it up. Okay. Anything else that you guys want to talk about before we get started? I will tell you that the last 4 lectures go really fast. It's all the same kind of math. We're talking about 3 different concepts, but it's all the same kind of math. And so it is very fast. In the past, I have gone through all 4 of those in one lecture period just because people didn't want to have class again. So when we got to it, we did all 4 of them in one lecture, and then they took some time off. So that can happen. So just so you know. All right. So any other questions? Okay. Now we're talking about complex ions today. Now we still need to talk about complex ions, but there are a couple of things that are in. Ooh, sorry, I need to move the schedule. That are in this lecture that we don't necessarily need to talk about. One is complex ion equilibrium and solubility. I've mentioned it, and I intend to just kind of go through it, but it's not something you need to pay a lot of attention to because it's not something that appears on the final anymore, and it's not something that I'm supposed to be testing you about. So I may skip it. Section 11, which is the application of the solubility product principle to quantitative analysis, really is outside of the scope of the course. And so I usually take time to talk about it because that's the kind of chemistry I do. But since we don't have time, we will probably skip those two. Now, the slides will still be there. I will post answers to those parts of it if anybody wants to look at it. But since it's not stuff that's required that we go over, I think we're only going to go through 2, 8, and 9 today. Does that make sense? Okay. All right. Now, one of the things that we've talked about, and that I've mentioned, is that we have to consider the effects of other things in the beaker when we talk about solubility. And one of those things that comes up is, what if I already have one of these ions in solution? So what if I'm talking about CaF2 and I want to look at how soluble it is? So if there's nothing else in it, we would have the solubility up here where it says pure water. But if I add NaF, which has an F ion on it, to this solution, you see that solubility drops precipitously. And that's because of the presence of that F. So if we have the F already present, then I'm not able to dissolve as much of the Ca. That's just how that works. We've put pressure on our system. It can't go forward as much because there's stuff on this side that is driving it backwards. All right. So that's what happens when we're talking about this, is we get an effect from the presence of whatever that other ion is, and we have to take a look at that. Now, that's the easy part, okay? So talking about CaF2 coming apart to give me a Ca2 plus the 2F minus. Again, if this concentration is already high, that's going to drive this reaction this direction. So it's going to push that equilibrium. Okay? That's Le Chatelier's principle, not part of it. So that's the theoretical portions of this. You know, the stuff we can talk about without any numbers. But we have to look at what effect that has on our numbers. So we've been doing these calculations using our Rice tables, and that will not change when we talk about having a common ion in it. So first I want to take a look at a Rice table for CaF2 when there's nothing there other than CaF2. Okay, this is the same kind of calculation that we've done before. I have a KSP that's given to me here. I know that initially I have none of this and I have none of this. So we're considering it before it breaks down. Every time it breaks down, I get one of these and two of these based on the stoichiometry. And that means that at equilibrium, I should have an x here and a 2x here because I had nothing to start with. And so if I look at the K for this, that KSP is equal to the concentration of the Ca2 plus times the F minus squared. So I have to square that because of the 2 in the stoichiometry. Then I can plug in the values that I have in the equilibrium row of my ice table. So KSP is then equal to x times 2x squared, which then will end up giving me 4x cubed. So that's one part of this. Now, that is equal to 3.9 times 10 to the minus 11th. So I can take that 3.9 times 10 to the minus 11th. Divide that by 4 to isolate x cubed. And then I can take and do a cube root on that. Anyway, thought I entered that, but apparently I did not. And that gives me 2.13 and some change times 10 to the minus 4. Now, since I had 2 sig figs in the number that I started with, my answer should be 2 sig figs. So again, I divided both sides by 4, and then I took the cube root. And that leaves me with an x value of 2.1 times 10 to the minus 4. So that would be equal to my Ca2 plus concentration. My F minus would be twice that because I have 2x. Okay. And for me, I just like to look at those when we do these comparisons. So I'm actually going to get a value for that just because it's going to make me happier. So 4.3 times 10 to the minus 4th. So those would be my equilibrium values for those ions from this solubility product. Now we're going to consider what happens if I add 0.05 molar NaF to the water before adding the CaF2. Okay, so now I've changed some things. I don't have the presence of any Ca, but I do have the presence of F, and that's a 0.05 molar. So that goes in there. Now, every time one of those dissolves, we still have the same process. So I add an X here, and I add 2X here. That still happens. Okay? When I go down, this is still my X. This would be 0.05 plus 2X. However, we always ignore the X portion because we make the small x approximation. It's not always valid, but we always make it. Okay, you're never supposed to use quadratics to solve these. Okay, so that's the situation that I have in this case. Because of that, I know that I can plug this in exactly the same way that I did here, and my KSP would then be equal to x times 0.05. That can be set equal to the 3.9 times 10 to the minus 11th, and that's 0.05x. I divide both sides by the 0.05, and that should give me the x value, which is how much Ca can dissolve. Okay, so and that gives me 7.8 times 10 to the minus 10th. That's a lot smaller than what I had before. And that's because of the presence of the F minus. So we can now look at what is the actual mathematics that goes with this. And you can see the effect of putting in a common ion. Okay. Again, that is because if I add F, then the amount of Ca has to go down because that thing is a constant. So it doesn't matter where I get that ion from, it still affects the equilibrium that exists with CaF2. So are there any questions on that? So what I've asked for here is to look at the solubility of aluminum hydroxide on its own and the
So sorry,
solubility. Go ahead.
I do have a question about the last one.
Yep.
Because like based on the formula, the KSP is the concentration of Ca times the concentration of F squared. But you didn't square the 0.005 and that concentration right there. Like,
Damn it, I forgot. That is totally my bad.
okay, so okay. So it's like, I mean,
Sometimes I do stupid things, and let me amend that. That is a very common mistake. So that is something I should not have done.
it still
Thank
like
you for
follows the same like formula, right? So like
That's
whatever.
correct.
Okay.
Yes. So, and I will fix that math.
Thank you. Sorry.
I am so sorry about that. Not that one. So, slightly different. And again, I apologize for that. Unfortunately, that is one of the very common mistakes, because we do have to square that concentration when we put it in. That is necessary. And did I create more questions with that?
Oh, it makes total sense now.
Okay. All right. So my question to you, would you like to run through another one? Do you want to have a few minutes to look at this and then we'll go through it?
Yeah, just give us a few minutes. We look at it and then maybe work it together.
Yep. So I will give you until 10:30 to look at this one. Okay, so I took the time to write the rice tables for the two of these and the reaction that we're looking at. So this is AlOH3. I know that Al is 3 plus because of his position on the periodic table. If I can't remember that, then I can look at the KSP table and see that it has AlOH3. So that's another way that I can do that. So that's the dissociation we need to look at. That becomes an Al3 plus 3 OH minus, and that means that my K is equal to that Al3 plus concentration times the OH minus concentration cubed. So I wrote that down so that I could set up my rice tables. Initially, when we're talking about this, just the solubility in water, we have none of either of these. So we start with 0. Every time I break this down, I get 1x here, and I get 3x here. And so at equilibrium, I will have an x and a 3x. I would then plug that into the KSP, which has a value of 1.8 times 10 to the minus 33rd. And that's equal to that x times the 3x cubed. Okay. So doing some simplification, this ends up being 27x to the third times another x gives me 27x to the fourth. So that is the thing that I need to work with on this side. I can then divide both sides by 27. So 1.8 negative 33rd, and I can divide that by 27. And that gives me 6.67 times 10 to the negative 35th. And I just put the line over it to indicate that it's repeating. So that's what x to the fourth is equal to. So I need to take the fourth root of both sides to get x by itself. And if I am to do that, I would take that lovely answer, I would put it to the 1 divided by 4 power. And that gives me 2.86 times 10 to the minus 9th. It is 3 sig figs because the number that I started with was 3 sig figs. So that should be x equal to, and I'm just moving it up, 2.86 times 10 to the minus 9th. And of course, that is the value here. And if I wanted to solve for that OH concentration, I would need to multiply that by 3. And that would give me 8.57 times 10 to the minus 9th. So I've now arriven at all of my equilibrium concentrations, right? Do the math, get the x. That goes in for the Al3 plus, and multiply by 3 to get the OH minus. Everybody cool with that? Now, if I set this up for the presence of 0.5 molar NaOH, instead of being a 0 here and a 0 here, this becomes 0.5. We still have the same change. So we get an x there and a 3x there. At equilibrium, this would be x, and that would be 0.5 plus 3x. We assume the x is small comparative to that, and it is. So I know that that's a good assumption to make here. Again, it's not always, but that is true here. So I have done that. I can then plug those values into the K expression that I had, as I did previously. So 1.8 times 10 to the minus 33rd is equal to that X value times 0.5 cubed. So I will divide both sides by the 0.5 cubed. So 1.8 second E negative 33rd. I divide that by 0.5. Cubed. And that gives me 1.44 times 10 to the negative 32nd. So with the presence of the 0.5 molar NaOH that we have, that also gives us the 0.5 molar OH, then the solubility on this goes down to 1.44 times 10 to the negative 32nd. Okay? So we see radical differences when we have a common ion. All right? So that, and again, that goes back to, that pushes that reaction back towards the reactants. I cannot get as much to dissolve, and therefore I won't get as much of that ion into solution. Okay? Any questions about that? So, comfortable enough for me to post this one. Okay,
Yep.
then I will do that. I will do that with this one as well. Good Lord, how many of these did I put in here? So one other, a couple other things that we have to remember. Okay, not only does the presence of the common ion affect the solubility of the salts, but it can also change the properties of the solution. So if the solution is a weak acid and we add the common anion, then we form a buffer. So if we had an acid that we were working with and we added more of that conjugate base, we're now in a situation where we've got a buffer to start with. And so that can change the math that we need to do. Right? The solution itself will be less acidic than it was because the acid is less soluble. Okay? So if we can't get that thing to dissolve, we're not going to have as much H+, and therefore it's not going to be as acidic as it was. And the solution is able to buffer the additional base or acid if we were to add it, because we've now formed a buffer. Okay? Common places where we see this is when we're talking about like CaF2 going to give us Ca2 plus the 2F minus. One of the things that we have to remember is that this F minus messes with the pH. So that F minus can react with the H2O to give me HF and OH minus. So depending on how much we've put in, that can be a significant effect on what that pH is. And we would have to consider this solubility to determine how much of it actually stays in solution if we were really going to calculate it. Now, that is not something you're going to get asked to calculate, because that's multiple equilibria that we have to look at, and that's not what we're doing. But you need to be aware of that, because it may change what you're looking at if you do this in the lab. Okay, so there are other effects that can happen. And of course, my general comment is, once we start looking at beyond one reaction, there's a lot of math that goes into that, and there's a lot of considerations that go into that. So keep that in mind. Okay? Now, this is just a statement about Le Chatelier's principle. So whenever a weak electrolyte and a strong electrolyte containing a common ion are together in solution, the weak electrolyte ionizes less than it would if it were alone in solution. So that means whatever's less soluble is not going to be able to go into solution as well as the one that is more soluble. Okay, so that affects everything that we look at. This is really just another statement of Le Chatelier's principle, because we'll get that common ion, it will drive that reaction backwards. Okay? So we can talk about the effect of acetate, adding that ion into an acetic acid solution. So acetic acid, CH3COOH, that should give me an H plus and a CH3COO minus. But if I add sodium acetate, where I'm adding this ion from another source, then what that means is that in my initial Rice table, I already have the concentration of this CH3COO minus from here, and therefore I'm not as able to dissolve the acetic acid. So again, we would have a less acidic solution because of that. And that's driving this reaction right here backwards. Okay? So I do have a couple of acid-base examples. These are no different than what we have already done. Do you want to do one?
You got time?
We can do one, sure. So if we can, what's the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter solution? Okay. So I have 3 moles of both of these, and it's a 1 liter solution. So that means that I initially have 0.3 molar here, and my acetate is also 0.3 molar. And I have none of that H plus. Okay. When this one comes apart, that's still going to be a minus X. That will give me an X here, and this will be a plus X as well. Sorry, that row is plus X. I always get ahead of myself. So that's plus X as well. And so here I have my 0.3 minus X. This is just X. And this is 0.3 plus X. If I can make this small X approximation there, I can also make it here. So in both cases, we will make that small X approximation. And so what we'll be putting into our K will be the values that I see there. So for acetic acid, that's my reaction. My K for that, which of course is a Ka, is equal to the concentration of the CH3COO minus times the concentration of the H plus divided by the concentration of CH3COOH, product over reactant. Since that's what I'm looking at, my Ka is going to be equal to the CH3COO minus, which is 0.3, times the H plus, which is X, divided by the concentration of the CH3COOH, which is 0.3. And that's equal to 1.8 times 10 to the minus fifth. Okay, so if I am solving this, those both go away, gives me X is equal to 1.8 times 10 to the minus fifth. From a Rice table perspective, that's exactly what you're looking at. And so your H plus concentration would be the negative log of the Ka. And my head is going, wait, negative log Ka, we talked about that, didn't we? Yeah, we did. We had pH is equal to pKa plus the log of the concentration of the base over the concentration of the acid. That's the Henderson-Hasselbalch equation. And if we set this up, we want to solve for pH or H plus, that's equal to the negative log of that 1.8 times 10 to the minus fifth plus the log of 0.3 over 0.3. The log of 1 is 0. And that means that your pH would be the negative log of the Ka. So that's exactly what we're talking about. So I can solve it either way. Doesn't matter. It's entirely up to you how you want to do that. But Either way would work. Questions about that?
So can we use that formula if the concentration is the same for acetic acid and its conjugate base?
Well, you can use it there, and you can use it if they're like a certain level different. So what they say is as long as it's not tenfold times, so as long as this one isn't like 0.03 and this is 0.3, then it will work. When it gets to be that small, it creates some issues in the math, and that doesn't really work that well. But of course, your buffer won't work that well either. So that's normal. So it matches the behavior we see in solution. Yes. So as long as you have a buffer situation, doesn't matter what they are, we can use the Henderson-Hassel box. Okay. Part of that is just knowing when you have a buffer situation. And again, it is never wrong to do it with the right. So other questions on that? This could potentially show up in the form of, hey, we're working with this acid or this base. I add some of the conjugate acid, conjugate base, or I titrate that solution, and now I've generated some of that conjugate acid or conjugate base, and now we have to find out what the pH is. So that's a situation that we typically see that. Okay? So there are a couple of examples. This one has no numbers on it, so I'll put that up before I post it because that was my bad. Same thing here. Apparently I wasn't paying very good attention to what I was doing. But I will plug in some numbers for those and post that. So the only thing I want to talk about in terms of this, and again, this is not on the test, this is not on the final, so I just want to talk about it a little bit. One of the things that we do in the laboratory is we'll go into the lab to try and test solubility. And if we do that with aluminum hydroxide, you would expect that you would get a lot of solid out of that because the KSP is extremely small. But what happens is if you do that and you add too much hydroxide, then the solid goes away. You form a complex ion like this, and those complex ions are actually soluble. So we have to be careful with that. So with a lot of these, so chromium does this, cobalt does this, copper does this, with certain ions, if we were to add enough, it would go back into solution. And this is why, is because it forms this complex ion. So it gets a charge on it, so it goes back into solution. Yay, it's fun. There are values, K values, for how often this happens. Okay, so you could do math with this as well. So that is always fun to do, but we are not doing that anymore. So I just want you to understand that some of these things, if you're continue to add things when you think they're going to be insoluble and they disappear, that's why. Okay. And of course, that affects your solubility, because if you formed this much, like with this reaction that we talked about, that goes to give me that Al3 plus 3OH minus. This has a fixed solubility based on that KSP value of 1.8 times 10 to the minus 33rd. But if we get to a point where we've added enough hydroxide, and this thing can pick up 4 of them, because that's the magic number for that one. So it picks up 4, then we start forming this AlOH OH4 minus. That then pulls both of these ions over here, makes them soluble, and so that means that that AlOH3 can dissolve more. Okay, so we're affecting both things by doing it. So just be aware that that can happen. And we can do it by adding more aluminum to this, or we can do it by adding more hydroxide to this. So either one of them will change it. And we sometimes do that if we need something to go into solution that doesn't want to go into solution. Okay? But we're not going to do any of those calculations. I will post them just if anybody's curious, but you will not be required to do them. That is not necessary. I think there was one more thing I wanted to talk about. So yeah. So
the complex ions are not going to be on the test?
The complex ions will not, and neither will this.
Okay.
So we talked a little bit about using selective precipitation to separate things. So, based on their KSPs, the one that's the least soluble will precipitate first. The ones that are more soluble will precipitate after that. Okay, that can be a very useful thing for us to do if we have multiple things in solution. So one of the things that happens very commonly is environmental cleanup. And so you go out and you collect a water sample and it has all kinds of crap in it and you have to clean that up. So if you're part of that remediation team, then being able to precipitate all of those things out so that you can filter them off and take them off is good. Okay, so knowing how to get those things out of solution is important. This is a slightly different way of looking at that. So we're playing with solubility here to be able to selectively get rid of some things. So if I were to take a sample of an unknown and I add HCl to it, what I could get out of that is AgCl, Hg2Cl2, and PbCl2. So those are the three things that precipitate with chlorine. Depending on how I add that, if I go slow enough, I can isolate those three things from each other if they're present. Now, there are some simple tests that we can do to see which cations are present. We are not allowed to do them in front of you anymore because they are somewhat dangerous, but there's this thing called a flame test. And so you can dip a wire ring into a solution, put it in an open flame, and see what color it is. That color is indicative of what cations are present. So I could know which ones are present in a very cheap, easy, simple test before I try and do this. And so if I have two of those things present, I can use that difference in the solubilities to collect both of them if they're there. We can then go and add to this something like H2S, because a lot of things are not soluble with sulfur. So we could get a copper ion, a cadmium ion, a mercury 2, because this one right here is mercury 1. It's always written as Hd2. Mercury 1 is always Hg2 2+. And so each one has a 1+ charge, but this is how it appears. So the second one is mercury 2, tin, and bismuth. So those are the things I could get out there. And again, if I know that I have two of those, I can do that slowly. I can be careful how I do it to isolate the ones that I need to isolate. And sometimes we need to do that so that we can quantitate how much was in it. If you're doing environmental cleanup, we normally have to do that because we need to know how much to charge these people for the mess that they've made. And that is based on how much of it was present. So that's something that happens a lot. Okay, so there are ways that we can use these things that we have just learned to help us to do identification and collection of things that are an environmental problem. So I just wanted to point that out because this is my kind of chemistry. This is called analytical chemistry, and I love it. So, but anyway, I'm done with that now. So, does anybody have any questions about the common ion stuff that is actually on the test? So these are the kind of questions that I would expect you to be able to manage with this. I would like you to take some time to look these over, and I will get this posted because I want to know if you are comfortable doing it. So that's important. I know you're not going to be overly ready to do it right now. That's why I think we should wait a little bit. Okay. Then I will do that. And that will take us out of this one. And we're going to start talking about redox. Now, as I mentioned, we're shifting gears a little bit. So we've talked about titrations that we did with acids and bases. We've talked about, aqueous solution equilibrium and precipitation of some of the things that will precipitate. We've talked about how we can calculate equilibrium concentrations, and we've talked about how we can deal with the rates of these reactions. So the rate versus the equilibrium, and we can solve for those things based on what we've done. Now we're going to start talking about a completely different kind of chemistry. And that chemistry is called redox. Okay. So let me flip this over. We're going to be talking about redox reactions, which was actually presented in your textbook in chapter 4 and the activity series. And then we'll be talking about redox reactions, the activity series again, and balancing redox. Okay, so that's where we're going. Redox reactions are called redox because it's an amalgamation of the two things that are happening. So we have oxidation of one of these things, and we have reduction of the other thing. And because you can't have one without the other, they cannot happen separately. We often put them as redox to remind ourselves that they have to occur together. This is a complete transfer of electrons. So we are taking something from like 0 charge to +2 or +2 to 0, depending on which way we're going. Okay, so we are now talking about changing charges. This is different than what we've done before. Okay, so now when we start talking about this, not only do we have to think about, okay, how many electrons were involved, but we also have to balance for charge when we start to balance these equations. So that complicates things comparative to what we've done before. Now, lose electrons oxidize. So if I oxidize something, I have lost electrons from it, so it becomes more positive. So Leo is lose electrons oxidize. That goes with grr, because Leo the lion goes grr, and gain electrons to reduce. So if I lose electrons from somewhere, they have to go somewhere else. So in this reaction right here, I've gone from a 0 state on both of these. So this has no charge. And when I come over here, Ca has a +2 charge and O has a -2 charge. Okay. So those 2 electrons were transferred from the Ca to the oxygen. And that's what we see here is those electrons coming off of this and then being added to the oxygen that's over here. Okay. So this isn't a, hey, I'm just going to throw some electrons out. No, unless there's somebody to take them, that doesn't happen. Okay. So are there questions on this part? All right. Now, we can talk about oxidation numbers. Okay. Oxidation number is related to how many electrons something has, but it's not necessarily its charge. So I don't like to talk about these things. I think it's not the best way to handle it, but if you're out on the internet, you may see this because some people balance equations using oxidation states. I do not. You will not learn that from me. If you choose to do that on the test, you need to tell me where you learned it. So if you learned it from some source on the internet, that's fine, but I need to know where. Okay, that's important. And if it came from something you did in high school and you remember it, then fine. Tell me where you went to high school and we'll talk about that. Okay. So if an oxidation number increases, that is oxidized. And if it decreases, that element is reduced. Okay. So again, lose electrons oxidized, gain electrons reduced. Now the sum of the oxidation numbers in a neutral compound is 0. Okay. The sum of oxidation numbers in a polyatomic ion is the charge on the ion. So if we were talking about OH minus, the sum of those oxidation numbers would have to be -1. The oxidation number of a monoatomic ion is the same as its charge. So that way, that works. So oxygen here would, be a -2, that works in those cases, okay? But that's only if it's a monoatomic ion. So something like calcium. And so it would have a +2 charge. Its oxidation state is therefore +2. Oxygen has an oxidation number of -2, except in a peroxide ion, in which case it has a -1. So remember that we have something like H2O2, and that charge on this oxygen is actually -1. So charge is -1, oxidation number is -1. Hydrogen is always -1 if it's bound to a metal. Okay. And +1 when it's bound to a non-metal. So in the ammonia case, this would be a +1. I'm trying to think, that goes over the other one. And I'm trying to think of any good metal hydrides. Tin makes a hydride, so that's SnH2. And of course, in this case, the hydrogen is -1. Okay, so that is one I know of. There aren't a ton. They're usually used in like semiconductor work. So fluorine always has an oxidation number of -1, which is again its charge. So that one's good. The other halogens have an oxidation of -1 when they are negative. But they can have positive oxidation numbers, most notably in oxyanions. So if it's attached to an oxygen, that can happen. Oxidation numbers can be fractions as well as integer values. So those are all the rules that go around our oxidation states. All right. It's a lot. Short form, hopefully a little easier. Elements are 0, monoatomic ions equal their charge. F is -1, O is -2 unless it's a peroxide, in which case it's -1. H is +1 unless it's a metal hydride, and then it's -1. And the sum of all oxidation numbers equals the overall charge. So I found it easier when it was a little condensed. So we can predict oxidation numbers based on what we've been talking about. So let's talk about that. And let's start with O2. What would you expect the oxidation number to be for O2?
-2.
It can't be.
-4.
Actually, it's not. And the only reason for that is this is the elemental form of oxygen. And so its oxidation state is 0. 0. All elements are 0. If it was a -2, then that thing would have a -4 charge. It doesn't. So the oxidation state has to be 0. So you got to watch out for that. For our diatomic gases, it gets a little confusing. Okay. If we talk about H2O2.
-1.
So our oxygen is -1 there, and our hydrogen is a +1. +1 there, -1 there. Cool. How about NaF? We had a rule about F. What was it?
Oh, -1.
Yeah. F is always -1. Na, because he's in the first column, should be a +1 because that's his charge. Monoatomic ions would be the same as their charge. Okay. H3PO4. Okay. So let's start at the beginning. Let's talk about the oxygen. So it's not a peroxide. So my oxygens are going to be -2, right? So I have -2 on those oxygens. That's their oxidation state. And there are 4 of them. That gives me a total of -8, 4 from the oxygen. Okay. My H, because it's not bound to a metal, should be a +1. There are 3 of them. So we then have to add the 3 from that. And that leaves me with an overall, at this state, -5. Does everybody agree with that math? And how I got there?
Yeah.
If this is equal to -5, but I know that this has to be 0, that means that the oxidation state on phosphorus has to be a +5, because that's the only way I can make it neutral. So some of these things we find by inspection. Okay. Now, there are a bunch more of these, and I understand that they're sort of important if you're going to use the oxidation number method for balancing your equations. As a chemist, since I have taken this class, I have never been asked what the oxidation state of something was. So while there are more, and I'm willing to post those, I don't know that we should spend a ton of time talking about it. And I hope that makes sense why. My husband's an organic chemist. He's never had to think about it either, because we've had that conversation. So cool with that. So that is how we would find an oxidation state if we were asked to do so. If I were to ask you on a test, it would probably be something that we had a rule about. So, and I might, but I might not. Because again, I would have to grade it, and I hate doing that. So let's talk more about oxidation and reduction. So if I look at this zinc, it's in its elemental state, and so it has an oxidation state of 0. When it comes to the other side of this, we have 2H+, right? And the reaction gives us, as products, Zn2+ and H2. So I know that I have taken 2 of the electrons that were on this zinc and transferred them to the 2 hydrogens to make H2. And therefore it has lost 2 electrons. So lose electrons oxidize. Zinc was oxidized. This one gained those 2 electrons, and so this was reduced. We always talk about what was oxidized and what was reduced on the reactant side. We never talk about it on the product side, because we want to know what happened to it. So we always talk about that on the reactant side. Okay? Species is oxidized when it loses electrons. Zinc loses 2, forming a Zn2+. So lose electrons, oxidized. Species is reduced when it gains electrons. H+ gains an electron, forming H2, because there's 2 of them. So that was reduced. Now here's where the confusing part comes. And I don't like this. So put Leo the line goes grr. So again, lose electrons, oxidize, gain electrons, reduce. There is another one that I'm familiar with, and that's oil rig. So oxidation is loss, reduction is gain. So that's what that stands for. I like thinking about the line. Now here's where it gets complicated. An oxidizing agent causes something else to be oxidized. and a reducing agent causes something else to be reduced. So if I am the species that caused your oxidation, I am the oxidizing agent. In this case, the species that caused the oxidation is the one that was reduced, and that's this guy right here. It is the species that caused reduction in something else. So when I think about that, it's an agent, it did it to something else. Okay, so there's a difference between what happens to me and what I did to someone else. The reducing agent is the one that itself was oxidized, so it caused reduction in something else, and so this is my reducing agent. Did that confuse the heck out of me? You bet. It absolutely did. And so in my head, I built this little process where I look at the thing and I say, okay, lose electrons, oxidize, gain electrons, reduce, decide which one happened to it. Then once I know what happened to it, I know it must have caused the other thing to something else, and therefore I can assign it to that. That's how my head works with this. It's probably not the most efficient thing, but at least it worked for me. So, does that make sense? It is incredibly important that you understand the difference between these terms. So flashcards would be helpful. Going over that over and over again would be helpful because you are going to be asked when we do some of these things, what was oxidized? What was reduced? What was the oxidation agent? What was the reducing agent? And that will be in the context of a lot of the other things we're talking about. So you need to make sure that you have those terms clear. Okay? Questions about this part? So, oxidation and reduction. We want to identify what's been oxidized, what is being reduced, what's the oxidation agent, and what is the reducing agent. Okay, so I'm going to look at chromium. It goes from Cr plus to CO3 plus. So it has lost electrons. If it has lost electrons, it was oxidized. So chromium was oxidized. Tin goes from 4 minus to 2 plus, and so we have therefore gained electrons there. Okay? And that means it was reduced. Sorry, writing it in the wrong place. Cool with that part. Now, because this caused this was oxidized, that means that it caused the reduction. It is the reducing agent. And again, since this was reduced, it caused the oxidation. This is the oxidizing agent. Are you cool with that? So let's take a look at the next one. And I like to start with the one that's neutral because it's easier for me to see what happened to it. Just how I do things. So I start with the Fe. The Fe here is 0. I know that there's no charge there. So when I go to a 3 plus charge, that means I've lost 3 electrons. Lose electrons oxidized. When we look at the mercury, we've gone from a 2 plus to a 0. So I have gained electrons reduced. If I was oxidized, I caused the reduction in something else, I am a reducing agent. And if I was reduced, I caused the oxidation in something else, and so I'm an oxidizing agent. let's talk about this last one. So AS has no charge here. AS over here has a +3 charge. Okay? So it's gone from 0 to +3. That means that it has lost electrons. Lose electrons oxidized. Cl2 is a 0. Over here it has a -1. Okay? So gain electrons reduced. And again, if I was reduced, I caused oxidation, so I'm an oxidizing agent. And if I was oxidized, I caused reduction in something else, and so I'm a reducing agent. Okay? So it's important that you understand how to look at, like, I went from my, the neutral state and having no charge of any kind to being a charged species. That's one thing, and it's usually fairly easy. The thing with this one, because it's over here as a complete molecule, we have to remember to break it down and see what it would be. And of course, if I was to break AsCl3 down, because Cl is -1, then As has to be A +3. Otherwise, we wouldn't need as many chlorines. Okay? So, unless people want me to do the other two, I'm going to post the rest. I want you to take a little time to think about it. Okay? And one of the other things that we talk about is the activity series. Okay, this is what an activity series looks like. So this image right here is an activity series. So if you were to see one, this is what it would look like. Now it may not look exactly like this. It doesn't necessarily have the arrow that says reducing strength increases, okay, because we don't like to give that away. You might see this without that. Things that it talks about is these can react with cold water to produce H2 because they're better reducing agents. I don't need the temperature to make it happen. This can react with hot water to produce H2, so I need the energy to do it because I'm not as good of a reducing agent. This reacts with acids to produce H2, so if there is an H that is free, then I can do it. So I don't really have enough reducing ability to break things down, but if I have a free H plus, then I can do that. Okay? And down here, these do not react with water or acids to produce H2. Now notice there's this yellow line right here, and that's for H2 going to 2H plus 2 electrons. We had to set something as our baseline, okay? And for God knows what reason, they chose this reaction as the baseline. So we measure everything relative to that. So we would make a reaction with this thing. So against H2, sorry. Where'd I go? What the heck did I do? Sorry. I went too far. Yeah, so, sorry, back to where we're supposed to be. So, I would set up a reaction against H2, and I would see what happens. And I would measure the energy that, we'll talk about that later. But that would determine whether it's a better reducing agent or a better oxidizing agent. So that is how we would determine. Okay? So, H2 going to 2H plus 2 electrons is our standard against which we measure everything. Now, the expectation from something like this is you would be provided with the activity series, and you would be asked something along the lines of, which of the 4 things in this list could I react with steam to make H2? And only one of them would be in the region that can do that. So the expectation would be you would pick the one that is in the right region. So good multiple choice kind of questions. The other things we see are like ranking things in terms of their ability to reduce stuff. So there's a question over here. It says rank iron, magnesium, and lead in terms of reducing strength. So if I wanted to do that, I'd have to find Fe. I would have to find magnesium, which is Mg there. And I would have to find lead, which is Pb. Where's my lead? Which is right there. So in terms of increasing reducing strength, it would be lead, iron, and then magnesium, just because that's the order they appear in the table.
Is this the full table, or is just like an example of things that fall into this category?
So there are other versions of the activity tables, but they tend not to be big. So the thing that's on the last page of the exam handouts is not an activity series.
Okay.
It's related to it, but that's not what it is. So we tend to only see this in smaller formats.
So is that something you would provide us on the test if you do have a question like that?
You would get the picture, yes. I can't expect you to work for the picture if I don't give it to you.
True.
So. Would SN be able to reduce H2 in an acidic solution? Yep, I see it right here. So because it's in this group right here, it can act in an acidic solution to give me H2. So that would work. Okay. The elements that are higher on the activity series are more reactive, and they almost always exist as ions because they want to get rid of that electron so bad. There's a lot of drive for them to do that. So questions about the activity series, how you would read it, what kinds of things you might get asked about it, what we use it for. Okay. So I want you to take, and I'm going to give you 3 minutes to look at this and tell me answer these questions. So 3 minutes, not a lot of time. So Okay. Now, in the interest of time and not making you speak, I'm going to answer these. So, tell me the 3 materials most likely to be ions on the table. Well, that was the stuff that was at the top of the table. So that would be those 3. So lithium, potassium, and barium are the 3 most likely to be ions. What are the 3 items least likely to be on the table? Well, those are the least reactive. And so we're talking about gold, platinum, and mercury. So those were the least likely. So top of the table, bottom of the table. Can Mg react with water to produce hydrogen gas? Well, now I've got to find Mg. And so Mg is right here. It reacts with steam to produce hydrogen gas, not water. So that's a no. Can lead react with nitric acid to produce hydrogen gas? Well, okay. Lead is right here. He's in the reacts with acid to produce H2, so I'm hoping that means yes. Can Ag react with anything to produce hydrogen gas? Well, Ag is down here, and it says, do not react with water or acids to produce H2. So I don't know of anything that can do that. So while it might be theoretically possible with things that are not on this table, we can't talk about that. We can only talk about what's here. Can barium react with anything to produce hydrogen gas? Yes, it can. So the thing that it's specifically listed with is cold water. So it can do cold water. But turns out that if you've got something up here, it can also do this, and it can also do this. So as long as we're above the yellow line, all of those would work. So in theory, you could list this with cold water, hot water, and acid. So just so you're aware of that. But the only thing I really want is which section it's in, which is with the cold water. Okay? So questions about that?
I do have a question about that. I'm sorry, did you say cold, not hot? So that's the only thing that it will react with. But just because it's at the top of the list, it doesn't mean that it will react with everything else.
So if it's in this section, it can react with everything above the line. That's correct. But not if it's here. So this one, you need the hot water to do it. It can't react with the cold water. In this section, I have to only react with acids. I can't do anything else.
But the question was, can barium react with anything to produce hydrogen gas? And it's like, I guess the answer is yes. But if it wasn't a steam, would it still produce hydrogen or no? Or it would never make it there?
Oh, no, yeah. See, I listed both cold, hot, and acid.
Oh, I thought it says cold, not. Okay, I got you. Okay.
No, sorry. No, that's my terrible handwriting. Cold, hot, and acid. So all 3 of those are, reasonable answers. The only one I'd really be looking for on the test was the cold water, because it's the hardest to do.
Okay.
So I want the top one. So other questions about our activity sequence? Okay. So now we're going to talk about half reactions. And half reactions are a little bit different than what we've been shown, what we've talked about in the past. We often write the oxidation reaction and the reduction reaction separately so that we can focus on what is going on there. Okay. They're written in balance separately, and then they're combined. All right. So we'll use them to balance a redox reaction. So when we talk about the reaction between SN2 plus to get to SN4 plus, we know that we have to lose 2 electrons to do that. That's how that works. If I go from Fe3 plus 2 electrons, because there are 2 Fe3 plus, then I will get 2 Fe2 plus. Okay. And the only reason I multiplied this by 2 is because I wanted to see two electrons on both sides. Okay. So if I were balancing this half reaction without considering the one above it, I would do it just like that, because I only need 1 electron to get between the Fe3 plus and the 2 plus. Right? So that's a correctly balanced half reaction. Does that make sense? So we're always looking at the difference in charge when we talk about getting the number of electrons. So our half reaction method, which is the one that I teach, we make the 2 half reactions, the oxidation and the reduction. We balance atoms other than oxygen and hydrogen on both sides of the equation. Then we balance the oxygen and the hydrogen using H2O and H+. Okay, so we start just like a normal reaction. We've got to make sure that we have the right things on both sides, right? But now we can add stuff. And we can add H2O or H+. That's because we normally do this in acidic solution. Now, sometimes we don't. Sometimes we do it in basic. And so we will make a change for that if we're in a basic solution. The way that I was taught to do this was to balance it in acidic conditions and then change it if we have to. So you pay attention to that part later. And we add electrons to balance the charge. So now that we've got all of the mass balanced, we've got the same number of things on both sides, then you balance the charge. And it's the total charge on both sides of the equation, right? We would then multiply by a common factor to make the electrons in each half reaction the same. And then we would add them. We simplify by dividing by common factors or converting H plus to OH minus if it's basic, and we double check our atoms and their balance. Okay, so that's the process I'm about to go through. I'd like to make sure that people know that this is a set of steps, because as long as you do it as a set of steps, it doesn't get screwed up, really. I mean, sometimes it does, that happens, but we're going to consider the reaction between MnO4 minus and C2O42 minus. So the other species that I have here are the Mn2 plus and the CO2. Those are the products for this reaction. Okay, and I have to be told that. So you wouldn't be asked what those things are. I'm just going to add a note page. There we go. Now I'm going to come over here because I need to have some space to do this. So one of my half reactions is MnO4 minus going to Mn2 plus. That's one of them. The other one that I have is C2O42 minus going to CO2. Okay, so those are my half reactions, and now I've split them. All right. The next thing that I was told to do is to balance for anything that's not oxygen or hydrogen. So looking at this Mn reaction, I have one Mn here and one Mn here. So I'm good. Here, I have 2 carbons and 1 carbon. So I need to fix that. So I have to put a 2 out here. Now I have the same number of carbons. I don't have the same number of oxygens, but I have the same number of carbons. The next thing that we do is we use H2O to balance for oxygen. Okay, H2O is very available in these solutions. So if I have 4 oxygens here and none on this side, I'm going to add 4 H2O. Because that gives me 4 oxygens on both sides of this equation. And of course, that's added to the Mn2 plus, it's already there. Here I have 4 oxygens. Here I have 4 oxygens. So I don't need to add any H2O. Cool. I love it when that happens. Of course, when I added that H2O, I messed up the H+. So I got hydrogens over here now, and I don't have any hydrogens over here. I got to fix that. So I added 8 H's. So I'm going to add 8H. plus, again, because I'm in an acidic solution. So I will add that 8H plus there. Now, I always take a second now and look at this. Okay, I've got 1 Mn and 1 Mn. I've got 4 oxygens and 4 oxygens. I have 8 hydrogens and 8 hydrogens. I have 2 carbons and 2 carbons. I have 4 oxygens and 4 oxygens. So I am balanced for everything that needs to be balanced in terms of what species are on both sides. Now the question becomes, what is the charge balance? So when I look at this reaction, because this one is easier, I have a 2 minus charge on this side, and I have a 0 charge on this side, right? Cool. All I want to do right now is identify the charges on both sides of the equations. On this side of the equation, I have 2 plus. And on this side, I have 7 plus. Because I had 8, I subtract 1, that's 7. And now I know that they're not the same on both sides, and I have to do something about that. Well, I do that by adding electrons. And I have to add the electrons to the side that has the positive charge. So because this is a negative charge here, and this is a 0 charge, I would add 2 electrons here. Because then both sides of my equation have a 2 minus charge. So they are equal on both sides because that's what I've done. Cool with that. When I look at this side, I have 7 plus on this side. I have 2 plus on this side. So I need to add electrons over here because it's more positive. And the difference between those two is 5. So I would add 5 electrons. Because if I do that, 5, 6, that leaves me with a 2 plus, which is exactly what I have on the other side. Cool with that.
I'm sorry, I'm like extremely lost.
Where?
I don't know much from the beginning.
We're going
Like,
to do
what
this
is-
again. So let me finish this one, and then we'll talk about how you should approach this. Okay? Is that okay?
Oh yeah, go ahead. Sorry.
Okay. So now that I have electrons on both sides, I have to give away as many electrons as I take up. I have 5 electrons here, 2 electrons here. Lowest common denominator between the two of them is 10. So I have to multiply this equation by 2 to get to 10. And this equation by 5 to get to 10. Okay, so now I'm going to go through and do the multiplication. So that applies to everything. Why aren't you? It doesn't want to draw parentheses. There. 2MnO4 minus plus 16H plus 10 electrons will give me 8 H2O and 2 Mn2 plus. Now, it makes sense to stop right here and check that you didn't miss anything. So, do I have 2 MNs here and here? I do. Do I have 8 oxygens there and 8 oxygens there? I do. That's good. Do I have 16H plus or H? So I've got the 16H, I've got 16H. Cool. And I still have my 10 electrons, which is what I was trying to get to. Okay. So I have now established that I've kept the mass balance. That's what we call it, the mass balance. So I still have the same number of things on both sides. If I look at the charge on both sides of this equation, I have 2 minus plus 16 plus 10E minus. And if I do that, then I have 12. That gives me a 4+ on this side. Okay. Over here, I have 2 times 2 plus 4 plus. So I am still charge balanced as well. Okay. Now I have to do the other equation. Let me get rid of this because I have to multiply this equation by 5. So I have 5 C2O4 2 minus 5 times 2, 10 electrons. And 5 times 2, 10 CO2. So 5 times 4 is 20 for my, for oxygen over here, 20 oxygen. 5 times 2 is 10, 10 carbon. And my charge here, I have 5 times 2 minus is 10 minus, and over here, 10 minus. So does everybody see that that is balanced at this point? Again, we'll come back to how you should actually handle this. I wanted to make sure that we got all the way through one of these, and then we talk about it. Okay. So now I have the same number of electrons on both sides, so I know that this reaction can happen the way that it's written. Okay, if I put these two things together, it will work because I have the same number of electrons being lost as they are being gained. That's important. So now we add them and combine like terms. So I have 2MnO4 minus plus 16H plus 10E minus. Those are all my reactants in that first equation. I then have 5C2O4 2 minus, and that's all of my reactants. I have accounted for everything that is there. Now I need to look at my products. I have 8H2O plus 2Mn2 plus 10E minus plus 10 CO2. So all I have done is pulled everything into one equation. I find that if I try to add and cancel at the same time, I screw up somewhere. So I don't do it. So I will put everything into one equation, and then I will look at what I can cancel. The first thing you should be able to cancel is your electrons, because you worked to make sure they were the same. So I have 10 electrons here, 10 electrons there, they disappear. Okay. Then I look for anything that's a like term. So do I have H plus on both sides? Do I have H2O on both sides? With this, I don't, because I only had to do that with one of my half reactions. So that's the best I can do for simplification for this set. So if I take out that 10 electrons and I look at, okay, M, N, O, H, and C, and then charge. So I have 2 MNs on this side. I have 8 H2O. 8 plus 20, 28. I had to remember the oxygens over here. Almost forgot. Hydrogens. I have 16 on that side, and I have 10 carbons. Overall charge on this side of the reaction, I have 10 minus there. So 2 minus, 10 minus, and then 16 plus. Oh, 12. That gives me 4 plus for this side. Cool. Let's look at the other side. So with my H2O, I only have H here. So 8 times 2 is 16. So those match. When I look at my carbons, I have 10 carbons. So those match. I look at my oxygen, I have 8 there, and I have 20 there, so I have 28 of them. And that matches. I have 2 MNs, so that matches. Now I need to look at my charge to make sure that that works. 2 times 2 plus is 4 plus. So that's my end of process check to make sure that everything is balanced for mass and for charge. And now you're looking at me going, how the hell am I supposed to do that? I know that's what's happening. I get that. It's important for me to show the entire process once so that we can talk about how we break that down. Okay. So this is the way that this gets handled. All right. Now I'm going to come back here and I don't want that one. I want this one. So we're going to take a second look at this, starting with that first step, which is making our half reaction. Okay. So my first half reaction, and this is step 1, I have HCOOH going to CO2 because the MNs have to go together. So CO2 has to be associated with this. So that will go to CO2. My second half reaction is going to be MnO4 minus going to Mn2 plus. Familiar. Okay, so that's my first step, half reactions. The second step is to balance for anything that is not carbon or hydrogen or oxygen. So not hydrogen, not oxygen. So I'm looking at the carbons. I have 1 carbon here, 1 carbon here, so it's good. Now, do I need to write that again? No. Do I? I do. Why? Because that means I actually did that check. So if my check here is to make sure that I have the same number of carbons, I did, it's balanced, cool. Over here, we're looking for Mn, and so I have 1 Mn here, 1 Mn here, and so I'm just going to move that down. Okay, so that's what we did last time. Now, the next thing that we did was to balance for oxygen using H2O. We have to do it H2O first, then H plus, because we screw up the H every time we do this. So we have to do the oxygens first. Okay. So now I'm going to look at the oxygens that I have. I currently have 2 oxygens on this side, and I have 2 oxygens on this side. So I don't need to do anything about that. HCOOH goes to CO2. I do not need to add any water. Here I have MnO4 minus on this side, and only Mn here. Remember that we needed to add H2O for that. So I add 4 H2O to get the same number of oxygens on both sides. So now I'm balanced for oxygen and everything that's not oxygen, and I have my 2 half reactions. The next thing I need to do is balance for hydrogen. I added H2O, so obviously I'm going to have some balancing that has to be done. That gets done with H+. Again, it's acidic solution, so that's why we use H+, because I know it's around. I have 2 hydrogens that occur right here, but none over here. So HCOOH is going to go to CO2 plus 2H plus to give me those 2 hydrogens. Okay. When I look at my MnO4 minus, I added 8H over here. So I need to add 8H plus. And that still gives me Mn2 plus 4H2O. Cool with that. The next step, step 5, is balance the charge with E minus. We're now in a place where we've balanced for everything that's in those reactions, except for the charge. We haven't dealt with that. So we need to look at what are the charges on both sides of these things. So because I added 2H plus here and there's no charge there, this is 2 plus, this is 0. Now, I'm going to look at the other side before I deal with any of the electrons. Okay. Here, I have 7 plus on this side. Again, 8 plus minus the 1, and then 2 plus on this side. So difference between them, starting here, I need to add 2 electrons to the side that is most positive. So I'm going to add HCOOH goes to CO2 plus 2H plus 2E minus. And so if I double check the charge, it's still 0 on this side. And now we have the plus 2 and the minus 2, so it cancels out, which is exactly what I was hoping for. Okay, so charge is good. When I look at this one, I know I have 7 plus here, 2 plus here. Difference between them is 5. So I need to add 5 electrons to the more positive side. So I have 5E minus plus MnO4 minus plus 8H plus goes to Mn2 plus 4H2O. So now I have balance for charge and for mass. Both of my half reactions are completely balanced. But I cannot put them together unless I have the same number of electrons, and I don't. Here I have 2, here I have 5. So we run into the same situation that we did on the last one. So on step 6, we want to make the electrons the same. And again, I do that by multiplying this equation by 5, and this equation by 2. So once I've done that, I will have 5HCOOH going to 5CO2 plus 10H plus 10E minus. Okay. Just checking to make sure that I didn't make any mistakes. I have 5 carbons on my reactant side, 5 carbons on my product side. I have Dr. is 10 oxygens over here and 10 oxygens over here. And this is a net neutral with those things there. So that is fine. I've done that one correctly. Doing the next one. 5 times 2 is 10 electrons plus 2 MnO4 minus plus 16H plus 2 Mn2 plus 8H2O. Okay. And if I want to look to see that everything's okay, I still have 2 Mn's here and 2 Mn's here. I have 8 oxygens and 8 oxygens. I have 16 hydrogens and 16 hydrogens. And my overall charge, if I add all of this together, I have 12 minus plus the 16 is 4 plus. But I also have 2 times the 2 plus is 4 plus there. So I'm completely balanced. So now I have 2 half reactions with the correct number of electrons, i.e. they're the same. So I have lost as many as I have gained. So now I can add. So now I'm going to add all of these wonderful things again. I have 5HCOOH from this reaction. Over here, I have 10E minus plus 2MnO4 minus plus 16H plus. And that's all of my reactants. Now I look at my products. So I have 5CO2 plus 10H plus 10E minus plus 2Mn2 plus 8H2O. So this was my 7th step, was to add them. In that 7th step, I'm also supposed to cancel anything that is common. So again, I should get rid of my electrons because I have 10 here and I have 10 here. Unlike what we had last time, we have H plus on both sides. I have 16 here and 10 here. So I can cancel the 10 and leave 6. So I only have 6 protons left on that side. If I look at H2Os, I didn't add any H2O to this reaction, so I don't have them on both sides. Okay, so that should work because we've reduced everything the way that we should. So if you want to go back through and check that you have the same number of protons on both sides, you can definitely do that. Okay. Actually, this was 10 plus 6 and 8, 16. So I have 16 on both sides. Cool, awesome. That's what I'm supposed to do. Now, why did I walk through it the first time without showing you the steps? Because I wanted you to see how easy it was to get lost. I don't believe that this is a process where you should get lost. I believe that if you follow the steps and do them in this order and in this way, then you won't get lost. Now, why do I say this way? When I was doing it before, even though I've been doing this for years, I was losing things when I was trying to move things and cancel things and make sure that I multiplied it right. This gives me a better way to go back and figure out what the heck I did. So if there's a mistake down here, it's because of something I did here. So I can walk back and look at where did I make a mistake and how do I fix it from there. So it's not a situation where I have to start all the way over. I can go back and look at the work that I've already done to figure it out. Now, there have been times, and I'm not going to lie, there have been times that every chemist I know has missed something. They just don't see it. And so you missed a multiplication somewhere and you think that it's balanced, but it's not. And so you end up adding totally wrong number of electrons, totally wrong number of hydrogens, which screws up everything. There is sort of a pattern blindness that happens if you stare at this too long. The other thing I'll tell you is that every single one of us, if we get up and walk away, come back and go, how did you miss that? So sometimes that's necessary. It's difficult on a test, and I get it. But going to another question can help. Okay? So do you have questions about what those steps are? Because I listed them all out for you. So this was balancing in acidic solution. Let's see. This next one is balancing in basic solution. So let's talk about how this works. So chromium hydroxide, Cr, I think 3 plus. Yeah, wait, hold on. Yeah, 3 plus, OH minus. So that's going to give me CrOH3 plus bromine gas, which is Br2. Remember that that's one of our dimers. Gives CrO4 2 minus and Br minus. So those are the species that I'm dealing with. Okay, I need 2 half reactions. So one of them is going to be the chromium, one will be the bromine. I always do this in, if this was written first, it goes over here. That's the wrong species. CrOH3 is going to end up giving me CrO4 2 minus. And of course, my Br2 is going to give me Br minus. So that's my half reactions. So this is 1 half reactions. Next thing I need to do, balance for anything that's not O or H. So chromium, I have 1 of each. So I'm just going to write it down again because I like to make sure that I have it moved when I do it. I don't want to leave a bunch of space if I haven't made any changes, because then when I get to the bottom and I have to do other things, I might forget something. So, and that still goes to CrO4 2 minus. When we look at our bromines, though, I need 2 over there. So I have Br2 is going to give me 2 Br minus. Okay, so now I've got the same number of bromines. Cool. Next thing I have to balance for is oxygen with H2O. This equation does not have any, so I don't need to worry about this for one. I'm just going to keep copying. This one, on the other hand, has stuff. I have 3 oxygens on this side, and I have 4 on this side, so I need to add an H2O. Okay? So now I have the same, oh, and I shouldn't have done it there. Sorry. And of course, I still have my Br2 going to 2Br. So that's my third step. Now I need to fix the hydrogen problem that I've created. And of course, this one has no effect, so I can just write it one more time. When I do this one, I have 3 hydrogens on this side, 2 more, that's 5, and I have none over here. So CrOH3 plus H2O, CrO4 2 minus plus 5H plus. So that takes care of my H with H plus. Next thing I'm supposed to do is balance for charge. So this side of my equation has no charge. This side of my equation, I have 5 plus minus 2 is 3 plus. Okay, so overall this is 3 plus. This is 0, and overall we have a minus 2 here. Okay, so I need to look at what would I do there. I need to add 3 electrons to this side of the equation. So CrOH3 plus H2O. CrO4 2 minus plus 5H plus 3E minus. Br2 needs to have 2 electrons added to it so that the charge is equal. Okay, so now I have equal charge on both sides. Cool. Now the question becomes, could I add these as they exist? Answer is no, because I have 3 electrons in this one, and I have 2 electrons in this one. So I need to do something. I'll multiply that one by 3, and this one by 2. Then I'll have the same number of electrons. So 3 CrOH 3 plus 3 H2O goes to CrO4 2 minus, and that should have a 3 in front of it, plus 15 H plus 6 E minus.
Don't you multiply the first one by 2 and the other one by 3?
Oh, I screwed it up. Yep, thank you. Brain apparently not working today. I apologize. My dog is having surgery. I'm not doing well. So, but that shouldn't reflect here. But yes, that is correct. To CrO4 2 minus plus 10 H plus. And now we get 6 electrons, which is what I was hoping for. Looking at the other one, I have 3 Br2 plus 6 electrons to give me 6 Br minus. So I have the same number of electrons on both sides. Now I can add. Okay. So 7th step is to add. Two CrOH 3 plus 2H2O plus 3 Br2 plus 6 electrons will give me 2 CrO4 2 minus plus 10H plus 6 E minus plus 6 Br minus. Canceling things that are the same. So I have 6 electrons here. I have 6 electrons here. I do not have H plus on both sides. I don't have H2O on both sides because I didn't have to use that for the bromine expression. So that is my balanced equation. And again, I always come through at the end. I have 2 CRs, 3, 4, 5 oxygens, 3 hydrogens, plus 4 is 7 hydrogens, and 3 BRs. That's weird. Oh, I forgot to multiply. See? So when I did my count for hydrogen, I only counted 3 here, and it should be 3 times 2, which is 6, plus then the 2 there, which is 8, and that's still not the same. What the heck?
No, you're right, because you have 6 on the left side plus 4 in the water, so you get 10 altogether, and then you have 10.
I don't have 2. Oh, hydrogens. I'm counting hydrogens, not oxygens. Sorry. Every once in a while, when I'm trying to do the H2O, I get confused and I think I'm counting the wrong thing. So I thought I was counting oxygen. 2 chromiums, 8 oxygens there. I have no more, so. And that should be an 8 over there. Miscounted again. H, 10H, and 2B, 6BR. Oh, and that's 6BR too, see? Must remember to multiply. I have no net charge on this side, and so no, wait, yes I do. This one. No charge on that side. 4 minus, 10 plus, and then 6 minus, which gives me 0. Cool?
Yep. So when you say counting charge, you're only counting the charges that are there. Like you're not counting some that doesn't have. Like
Well,
that's
if it
why you
doesn't have
say,
charge, it's not part of the charge calculation, correct? So if it's a 0, I don't have to actually actively add the 0.
yeah, but now it makes total sense. I was like really struggling where were you getting all these numbers, but now I see.
So I made some very common mistakes when I was doing this, and I'm not quite done yet. So give me a second. Oh, let me finish it. Because what did we balance this in? That's an acid. Is it supposed to be an acid? It's not. It says basic. So the process that we go through is exactly the same. Exactly the same. Once we get rid of this, I'll show you how we fix it. So the problem with being an acid solution when you're actually in base is that I don't have any H plus laying, right? So I have to add the same number of hydroxide ions to both sides of the equation as I have H plus. So I add 10 OH minus on this side and 10 OH minus on this side. If I'm adding the same number to both sides, that doesn't change anything. What happens, though, when you have 10 H plus and 10 OH minus is that's 10 H2O. So these two combine to give me, instead of that, 10 H2O. And so now I can cancel the 2 H2O that are here. That will leave me with 8 over here. And if we go through and do the balancing again, they won't be the exact same numbers, but they should still be equal. So 2 chromiums there, 6 oxygens there, 10 there, so 16 oxygens over here. I have 6 hydrogens, and 10 hydrogens, and 16 hydrogens. I have 6 Br, and the overall charge on this side is negative 10. When I look here, I have 2 chromiums, I have 8 oxygens from there, 8 from there gives me 16. I have just there 16 H2 and then 6 Br. And the overall charge on this side, 4 minus, 6 minus, 10 minus. So that correction that I add at the end, then that's why I call it is the basic correction. Means that you add the same number of hydroxides to both sides of the equation as you have H plus. And then your H plus and your OH minus become H2O, and you can clean it up. So questions about that?
Nope.
I made a couple of very common mistakes. It's true. So things that I didn't do right. I didn't necessarily carry numbers down when I was writing the equations again. That's important. So you need to make sure that you carry those numbers with you when you do this. I didn't necessarily count correctly. So I had issues when I was counting here because I was applying the 3 to the hydrogen, but not applying the 2 that's out in front of it as well. So I thought I only had 3 hydrogens, but when I should have 6. So that's an issue. We have to make sure that we take care of that. I don't think if I did anything else. Oh, I did the thing that I do sometimes, and I put the wrong number in front of this equation and the wrong number in front of the other equation and was multiplying them incorrectly. Occasionally that happens. I have a mild number dyslexia, and so occasionally I will do that. It's something I need to watch for, but I don't always catch it until I'm trying to balance things. So that's another problem for me. So, but those are common things, is, forgetting to pull numbers down, forgetting to distribute the coefficients in front and the subscripts at the on whatever ions you have. Another thing that I've seen is sometimes people will leave the parentheses off of this. That is incorrect, because then you would have 3 hydrogens and only 1 oxygen. So you have to make sure that your polyatomic ions have parentheses around them. It will make you remember that that's what it's supposed to be. And it actually is not written correctly if you don't have it that way. So watch out for that. Now, I know that this is not sinking in well yet. I get that. That's why you have that on paper assignment that you were given. You've been asked to balance a few of these. I think there are 10. So if you run into problems doing that, let me know. Now, one other thing I want to point out before I let you go, because I know I'm over, I'm sorry. When we talked about this reaction rate here, this one, when we talk about this one, We balanced that, and we ended up with 10 electrons plus 2 MnO4 minus plus 16H plus going to 2 Mn2 plus plus H820, right? When we did that over here, we had it reversed. So we had 2 MnO4 minus plus 16H, once we did it, 16H2O plus 10 electrons goes to 8H2O plus 2 Mn2 plus. Why am I pointing that out? Because it doesn't matter which direction it is. It's always going to balance the same way. And we will talk about the fact that your exam handouts have some places where you can look to see if you already got a balanced equation for it. You won't always have them. Sometimes you will, sometimes you won't. Okay? So use your resources as you can. And if you've already balanced it, you can just tell me, see that other question, that's fine. You don't have to balance it again. And I do sometimes do that to try and save you some work. Because these take time. So questions, comments, problems. I know we're not completely through this lecture yet. And let's see what else we got. I'm just going to move your homework. So I'm going to change the due date on that, the Redox homework, just to make sure that you guys have had enough time to deal with it.
So the activity series will still be due on Sunday, but the redox reactions will be due later?
I will probably move that too.
Okay.
Because they're both based in Redox. So we talked about the Redox part or the activity series, and you could technically do it. But I'm going to move it anyway. It'll be easier if I move them both. Now, don't wait until the last minute, because then you get caught out. So you could do the activity series now, but it's not going to be due on Sunday. So questions, comments, problems. I should have the test grades posted today, and I will talk to whoever I need to talk to, and we will move forward. Okay? Also, if you did less than 70%, I will contact you so that we can set up a meeting to try and get you caught up. That's something I do as well. All right, guys. I hope you have a fabulous weekend, and I will see you on Monday.
Thank you. I did have a question about something we were working on earlier, but I don't know. I'm trying to find it in our slides right now. It was, I think, the acetic acid. Thinking about acetic acid.
So when we were talking about the redox portion of it,
I think it was after we went over the common
ions. Okay. Yeah, there is
a
redox.
Not redox. Okay, so that's why I can't find it.
Yeah, give me a second. I'll get back to that because I know what you're talking about. So we did an acetic acid in here.
The answer is like H is equal to negative log
of the Ka.
Yes.
Yes.
So that is like correct. How we leave it, like we can't do anything after that.
Well, you can calculate it. I mean, if you take the negative log of the Ka that you were given, you would have an actual value for it. I just didn't bother.
Okay, hold on. Yeah, if you could pull back up, because I feel like I'm just like missing something.
So yeah, so this is where we were. Again, we know that because these two are the same, x is equal to 1.8 times 10 to the minus 5th. Okay. So that's the concentration of the H plus. And if I wanted to find the pH, I would have to take the negative log of that 1.8 times 10 to the minus 5th.
And you don't have to do the log part because the other half, like the plus log over like 0.3 over 0.3, that just cancels.
That's it. Well, yes, this does cancel, but that's a different way to solve this. So this is one way to solve it, right? So you get the X value here, and then if you wanted pH, you would take the negative log of it.
Okay, yeah.
But this is the Henderson-Hasselbalch, and you can solve directly for the pH using the negative log of Ka plus the log of the concentration of both the acid and base. And since they're equal, this term is 0.
Okay.
So that's
Okay.
what all I wanted to show is that you could do it either way.
Okay, thank you. And then you said you'd be reaching out if like you had problems with the exam or like if we got like below a 70.
Yes,
Okay.
that's correct.
All right, thank you.
You're welcome. Have a good day.
Bye, you too.
Dennis, you're still here.
Oh yeah, I'm sorry. I'm trying to do that ClO2 reaction, which is
Which one?
the very next one. It says another example in acid. It was the ClO2 minus and then ClO2 plus Cl minus. You guys were talking, so I just like kept on looking at it.
Okay.
Thank you. I mean, am I good with the test? I haven't heard anything, so good.
I haven't announced nothing yet.
Okay.
Except for the general comment that I found some things that were way squirrely.
Okay. Did you see?
You were not squirrely.
There was like that few questions about it, but I guess.
Oh, that's right. You weren't here at the beginning. Yeah, so I have changed the point values on some of those. So the one table, there were 3 columns that you should have been able to answer without value. So those are the ones that I graded. The other 2 columns I did not. So there's that one. And then a couple of the questions that had some other issues, I turned them into bonus questions instead. So the overall point value is lower than it would have been, and there are more opportunities for extra credit.
Okay.
That's how I decided to handle it.
Yeah, I mean, I feel like I overstudied a little bit for the test. Like, you should have seen it. I like literally, my wife was making fun of me. I had like sticky notes like all over this thing on the wall, and she was like, "Would you just like use the bigger ones?" And they're like the tiny ones. They're like 2 by 2, and there's like squares everywhere.
Yeah. I could see why you might feel that way, because the test can only be so long. So you don't always get a great representation between equilibrium and rates. So
yeah, I feel like I did spend a lot of time on that. But that's just because I was like struggling a little bit with it, like just to kind of get the concept down.
Yeah.
But I think like I feel like I did enough. And then there were no pressure questions too, and there were like some on the homework, the
I told
KP
you
ones.
but I told you I wouldn't test you on that.
Oh, okay. Because that was just like another way to kind of look at things, So
Yeah, it is. And there were some questions in the homework because I need you to understand that it works the same way. So with pressures for all gaseous stuff, it works exactly the same as a concentration one.
makes sense. Alrighty. Well, have a great weekend.
You too.
I'll see you Monday then.
Yes, I will see you Monday.